Picture the strangest laws of the universe, the ability to be in multiple places at once, for objects to stay in sync light years apart, or for particles to also be waves. Now imagine a device that can tap into this strangeness and give us computing powers millions to billion times more than our everyday machines. One that can reshape how we solve problems, invent medicines, and secure our digital lives. Welcome to Demystifying the Physics of Quantum Computing, where we'll unveil the mind-bending physics behind qubits, superposition, and entanglement in everyday language, and discover why they're poised to rewrite the future of technology. Over 50 years ago, NASA sent humans to the moon with computers so tiny by today's standards that your modern calculator would outclass them. That smartphone in your pocket is millions of times more powerful than those mission-controlled behemoths. Still, that modern marvel is just scratching the surface. All the phones, data centers, and supercomputers on Earth combined can't hold a candle to what quantum computers might achieve. Think of Apollo-era hardware as a rickety wooden raft, and your smartphone as a sleek motorboat. Quantum computers could be our starships, unlocking entire galaxies of possibility no classical machine could ever reach. We'll start with the basics of how atoms and photons gave birth to quantum mechanics, dive into experiments that upended centuries of scientific conviction, and then move on to the 4 leading contender technologies for building quantum machines: superconductors, trapped ions, photons, and exotic topological qubits. Let's dive in. Let's start at the beginning, where ordinary physics meets the downright bizarre. The building blocks of matter are atoms. Typically, we imagine the well-known mini-solar system model, a nucleus in the center, electrons whizzing around. It's not entirely accurate. Any physicist would cringe a bit to hear that, but it's a decent mental placeholder. Those electrons, if you recall from high school, can jump between energy levels. They do so by absorbing or emitting a photon, a tiny packet of light. In the classical computing era, electrons play the starring role. Inside each transistor, tiny electronic switch, a flow of electrons creates an electrical on or off state, corresponding to a 1 or 0. When a transistor is on, electrons freely move through a channel. When it's off, that channel is blocked. This is what flips bits from 0 to 1. Billions of such switches act in unison in your smartphone, letting you scroll endlessly through memes or watch cat videos on your morning commute. On the other hand, photons are the quantum carriers of the electromagnetic force. They can act like waves, spread out, interfering with each other, forming ripples, or like discrete particles, each photon bounding along. The question often gets posed: which is it? A wave? A particle? The correct answer is both. To see why, step back to the year 1801. A British scientist named Thomas Young shined light through 2 closely spaced slits and watched, enthralled, as a striped pattern of bright and dark fringes appeared on a screen behind them. That interference pattern is the signature of wave behavior. The demonstration created a massive uproar because many folks still believed in Newton's idea that light was made of tiny bullets, particles. But Young's experiment told a different story. Light can diffract, overlap, produce bright fringes where waves add up and dark fringes where waves cancel. Then, decades later, people repeated the experiment with electrons. Full-blown matter. In principle, electrons ought to behave like bullets, right? Turns out, not really. Electrons and even atoms interfere like waves, the same as we observed with neutrons. What's even more spectacular is fire them one at a time, and even then, eventually you build up that same wavy interference pattern. The illusions multiply. Wave or particle, the electron is both, until you measure it. We see from the double-slit experiment that particles can act like waves, blending all possible paths until you take a peek. This wave-like behavior sets the stage for probability in quantum land, where we can't say the particle is at one place or another, only that it has certain odds of ending up somewhere. We all know coin flips are 50-50, dice are 1 in 6, and so forth. But quantum probability goes deeper. A quantum system might be, say, 60% heads and 40% tails, but with a twist. If you observe it too soon, you force it to pick one. Observing a quantum system literally changes what it does, a stark break from classical thinking. A regular coin toss is decided the moment it lands, but a quantum coin remains both heads and tails until someone looks. Hence the notion that quantum objects, like electrons or photons, carry these mysterious probability amplitudes, not definite outcomes, until measured. That sets up our next dimension of weird. Take a normal computer. At the hardware level, each piece of data is either 0 or 1. That's it. The fundamental building block is the transistor, controlling the flow of electrons. On equals 1, off equals 0. You can picture your smartphone as full of billions of these transistors. They're either talking or silent, but they never do both at once. Now, a qubit is the polar opposite. Qubits are the fundamental blocks of quantum computers, the same way bits are to classical computers. A qubit doesn't have to choose between 0 and 1 until the very last moment. Instead, it can remain in a combination of 0 and 1, both states at once, right up until you measure it. This fleeting property, known as superposition, lays the foundation for quantum's extraordinary speed-ups. The standard illustration of qubit is something called the Bloch sphere, like a globe. The North Pole might correspond to 0, the South Pole to 1, but a qubit can lounge around on any point on that sphere. Hence, the qubit can hold a combination of states described by complex numbers. If you measure it, you find either 0 or 1, with certain probabilities. This both states at once phenomenon might make you wonder, so do we just get infinite computing states? Well, not exactly. The real advantage emerges when we harness multiple qubits. They can do an exponential variety of computations in parallel, at least in principle. So how did we jump from electrons toggling everyday ones and zeros to the mind-boggling notion of qubits holding infinite possibilities? As it turns out, the journey took longer than half a century. Picture the 1940s and 50s, with entire rooms groaning with humming vacuum tube behemoths, each tube prone to blowing out like an ancient light bulb. These were the basic logical units of computations at the end of the Second World War. Then came the transistor, a speck of semiconductor that could switch on or off with minimal power and almost no wear. Invented by John Bardeen, Walter Brattain, and William Shockley, it kicked off an avalanche. By the 1960s, we had integrated circuits packing dozens, then hundreds, then billions of transistors on a fingernail-sized chip. Think of it as going from clunky mechanical gears to sleek, invisible switches, smaller than a grain of pollen. That jump slashed costs and catapulted us into the digital age. By the 1970s and 80s, Moore's law reigned supreme. Transistor counts on chips doubled roughly every 2 years, computers shrank, speeds soared, and the modern world was born. From email to video games to the smartphone revolution. But there was a major challenge lurking. Transistors rely on controlling electron flow in a channel. As these channels shrink to just a handful of atoms, electrons start ignoring our attempts to keep them locked in. They pull quantum stunts like tunneling, where an electron simply appears on the other side of what should be a solid barrier. Instead of a neat off or on, you get an unpredictable leak of current that scrambles the bit. Engineers have spent decades wrestling with these near-atomic scales, stacking more elaborate designs to mitigate tunneling and keep logic stable. Ironically, the quantum intrusion we tried to avoid gave researchers a bold idea. Why not embrace quantum mechanics and forge an entirely new computing paradigm? Scientists realized that if the universe is inherently quantum, perhaps we could store and manipulate data using quantum states rather than classical on/off. These special quantum bits, or qubits, could harness superposition to represent many possible values simultaneously, and entanglement to correlate qubits in ways classical bits never could. The transistor era laid a vital foundation, but quantum computing had its own turning points. In 1980, Paul Benioff, a theoretical physicist, proposed something bold: a Turing machine that obeyed quantum laws rather than classical ones. It was the first blueprint for a universal quantum computer. Benioff's framework cracked open the door, showing that standard logic gates might be replaced by quantum operation. Then, in 1982, Richard Feynman highlighted a core challenge. Classical computers struggle to simulate quantum effects precisely. His call to action was simple: build quantum hardware to handle quantum problems. Though it sounded radical, it struck a chord with researchers who saw classical methods falter on molecule and material simulation. Deutsch and a few others took Benioff's and Feynman's ideas and began shaping the earliest quantum algorithms. Though these routines were modest, they proved that qubits, employing superposition and entanglement, could solve certain tasks in ways classical bits never could. For quantum computing, this correlation unlocks the ability to handle computations in parallel, distributing the problem across entangled states. It's like choreographing a dance where all the dancers move in perfect sync, even if they don't talk. The result is an exponential scaling of computing power, at least for certain specialized tasks. That's why many quantum algorithms rely heavily on entanglement to deliver a speedup that no cluster of classical processors can. Having seen the power of classical computers, a question naturally follows. Why quantum? If bits and transistors can take us to the moon, power virtual reality and weather predictions, what more does quantum computers bring? Superposition is the concept that sets quantum computing drastically apart from its classical kin. Ordinarily, a bit must be either 0 or 1, like a coin landing heads or tails, but a qubit can embody both 0 and 1 at once, sitting in what's essentially a weighted mixture of both states. Think of it as a coin spinning in mid-air, capturing every possible face in the blur. And it's not just a random guess. The mix is precisely defined by mathematical amplitudes, which combine like waves. The moment you measure the qubit, it collapses to a single outcome. Until then, it harbors all the possibilities in superposition. This wave-like property means a handful of qubits can encode a staggering array of parallel computations. In principle, that's what lets quantum computers explore huge solution spaces at lightning speed, especially for tasks like searching massive databases or factoring unwieldy numbers. If superposition is the reason one qubit can handle more than just 0 or 1, entanglement is the reason multiple qubits working together can achieve feats a classical machine can't even approximate. Entanglement ties 2 or more qubits into a single system, where the state of each qubit depends on the state of the others, no matter how far apart they might be. In classical terms, that's like magically linking 2 coins, so if you flip one, you instantly know the outcome of the other, even if it's on the opposite side of Earth. Physicists, Einstein included, once found this concept unsettling, calling it spooky action at a distance. But countless experiments confirm that entanglement is real and fundamental to the quantum world. When qubits are entangled, measuring one qubit's property, say it collapses into 0, influences the other qubit's state, which might collapse into 1, with no classical exchange of signals. Think about how unstoppable this might be if done at scale. Researchers define quantum supremacy as the point where a quantum machine outperforms the best-known classical computers at a specific, well-defined problem. In 2019, Google claimed to have hit that milestone with a 53-qubit superconducting chip called Sycamore, which executed a random sampling task in around 200 seconds, something they estimated would take 10,000 years on a classical supercomputer. Critics questioned the margin, but the demonstration was a loud statement. Quantum machines can, under the right circumstances, pull off feats classical ones can't. Think of it as a bold glimpse into a new computing frontier. like sending a rocket just past Earth's atmosphere. We haven't colonized the stars yet, but we showed we can leave the ground. With that, we pivot from the why to the how, exploring the diverse physical forms a qubit can take. Because building a single qubit is hard, building hundreds or thousands is even harder, and controlling them all might be the greatest engineering challenge of our time. In the next chapter, we meet the main players forging this quantum hardware revolution. Now that we understand what qubits are in theory and why we need them, the question becomes, how do we make them? What's the physics behind actually implementing qubits? To make qubits real, we need hardware, some physical platform that can cradle these delicate quantum states long enough to do meaningful work. The aim is to store and manipulate superpositions and entanglements in real physical matter. Surprisingly, there's no single one-size-fits-all solution. Instead, multiple approaches compete, each harnessing quantum weirdness in a unique way. Some labs, like Google and IBM, build superconducting circuits that act as artificial atoms when cooled near absolute zero. Others, such as IonQ, trap single ions in a vacuum with precisely tuned lasers. A third cohort directs single photons with optical fibers. Next up, we go into the 4 leading hardware models to implement qubits and the physics behind them. The first method is superconducting qubits, today's mainstream star. Here we make loops of superconducting metal, aluminum, or niobium that become quantum at extreme cold. By hitting these loops with microwave pulses, you drive them from state 0 to 1 or superpositions in between. Google's Sycamore chip used 53 such qubits in its 2019 quantum supremacy test. IBM's Q systems are similarly built. The major advantage of these devices is to run gates fast, on the order of nanoseconds. However, each qubit demands individual control lines, plus serious shielding from vibration or stray radiation. Scaling beyond a few hundred qubits is difficult. Think of it as a short-distance runner. It moves quickly, but easily tires. Even so, superconducting is the most advanced in terms of real-world demonstrations. Google, IBM, and smaller startups keep pushing the qubit counts higher using superconducting qubits. Another approach is trapped ion qubits, which includes mastering atoms with lasers. Trapped ion qubits have a distinct advantage. Each ion is a single pristine atom, like terbium or calcium, boasting very long coherence times, sometimes seconds or minutes. That grants more time to do computations before decoherence sets in. The flip side, however, is that laser-based gates can be slow, measured in microseconds or milliseconds. And scaling to thousands of ions means orchestrating a sophisticated laser light show. Companies like IonQ, Alpine Quantum, and Quantinuum champion trapped ions. They say it's easier to implement error correction because each qubit remains stable, though building massive arrays of vacuum chambers remains a big engineering quest. Still, from a fundamental standpoint, ions are incredibly uniform. Every ytterbium ion is identical, removing a headache that plagues other hardware. Light is another candidate for qubits. After all, photons can zip across continents through fiber optics, making them perfect for quantum communication. A single photon's quantum state, often encoded in its polarization or phase, serves as the qubit. Special sources generate these photons one by one. Beam splitters and mirrors steer them into paths that can create superpositions. Nonlinear crystals or other optical components facilitate entanglement, letting 2 photons correlate in quantum ways. Companies like Xanadu or PsiQuantum hope to scale that concept into full-blown quantum computing. The big perk is potentially no cryogenics needed. Photons seldom require deep freezing. Also, they rarely interact with background noise. But that's precisely the problem. Photons are so non-interacting that entangling them in large numbers is tough. You need nonlinear materials or elaborate interference setups, so it's still an uphill climb to handle thousands or millions of photonic qubits. Yet photonics could excel at specialized tasks like secure communication or certain sampling problems once we crack large-scale entangling gates. A final mainstream approach is topological qubits. In topological quantum computing, qubits aren't stored in simple energy levels but woven into the very geometry of special materials. Picture anyons, weird quasi-particles that emerge in two-dimensional systems. When you braid these anyons around one another in a particular pattern, you encode a qubit's information into their paths. That's powerful because local noise, like a stray vibration, can't easily corrupt a topological qubit. The data lives in the braiding rather than a single fragile state. This could drastically reduce error correction overhead. If you physically move the anyons to perform gates, you might skip many complexities. Finding stable anyons, however, is proving tricky. Experiments are ongoing with no definitive large-scale demonstration. Microsoft is experimenting with the approach, but real breakthroughs remain elusive. If successful, topological qubits could overshadow other methods by natively resisting noise. If not, it stays a fascinating long shot. For now, superconducting and trapped ions appear the most advanced. Photonics and topological qubits sit on the frontier, each with a unique promise. If you like this episode, check out the other episodes in our series on demystifying quantum computing with everyday language. We've come a long way, from the wild quantum landscape of wave-particle duality to the real hardware that makes qubits tick. But there's so much more to explore. In the next episodes, we're going to dive deeper into the how and why of quantum computation. We'll translate the mind-bending mathematics of superposition and entanglement into everyday language, show how engineers wrangle control systems to keep qubits in line, and explore the unsung heroes of quantum error correction and algorithms. Finally, we'll talk about what it truly takes to program these futuristic machines and why the biggest breakthroughs may be just around the corner. So stay tuned. The quantum journey is far from over, and the next steps promise to be even more thrilling.